Hello everyone. Today's lecture is about finding lambda and x from the following four equations. So all let me so we have equation A, x double prime plus lambda x equals 0, and x0 equals 0, xl equals 0. And then B problem, we have the same equation, but condition, boundary condition different. So x prime 0 equals 0, x prime l equals 0. And then problem C, you have a mixed of A and B, right? So x0 equals 0, x prime l equals 0. And then problem D, x prime 0, xl 0. So just slightly different, okay? So the problem here, so I will give definition here. If, let's see, if there is solution, non-zero solution, so here, definition, if there is non-zero solution, okay, non-zero solution, xx, okay, corresponding lambda value, so lambda x, let's see, let me erase, such that satisfying x is a non-zero solution and corresponding to lambda satisfying A or B, A or B or C or D or, okay. Then we say that lambda is eigenvalue, and x is eigenfunction, the corresponding eigenfunction of the problem. So that's why we call these problems are eigenvalue problem. Okay, so these are ODE equations. So these four type of eigenvalue problems will be used to get the Fourier series solutions. Okay, let's see. Let me try to find lambda and x from A. So consider A. So let me try to find x in A. So we have problem x double prime x plus lambda x equals 0. I have x0 equals 0, x l equals 0. By ODE, the first case, suppose we case 1. So case 1, so if lambda equals positive, okay? So if lambda is, let me call negative first. So suppose lambda is negative. In this case, you can write down lambda equals a squared A should be positive. So you can write that in this way. And then we have equation x double prime x plus a square xx. Okay. And you know that in ODE, in order to solve this, we need the auxiliary equation. So auxiliary equation will be r squared plus a squared equals 0. So you got r equals plus minus ai. Okay. So then if auxiliary solution is this one, then the general solution of x, this equation will be a times cosine alpha ax plus b times sine ax. Okay. And we want x is a non-zero solution. And then we use condition x0 equals 0. So since x0 equals 0, I'm sorry, I got the wrong. So I'm doing positive case. Oops. I try to have negative, but I'm using positive case. Okay, just there's a positive case. x0 equals 0, you plug in here. So x0 would be a. Okay, a should be 0. Okay, a should be 0. So a equals 0, they have a b sine ax. Okay, and then since we're looking for non-zero solution, okay? So we want to get eigenfunction, non-zero solution. Okay. Since we want x is a non-zero solution, so that implies b cannot be 0. Okay, we don't want b. Let me erase here. We don't want b equals 0. So b is non-zero. Okay, because we want eigenvalue problem that is non-zero solution. Oh, this is not what I want. Oops. Okay, so let me rewrite. So non-zero solution. Solution x. Okay, so and also we condition the condition x is also xl equals 0. That implies 0 equals xl. Then you put b sine al. Okay, so b is non-zero. That implies sine al equals 0. So that implies al should be k pi. Okay. So, but we want a is positive. So since we want a and positive, then k is a natural number. 0 from 0. K pi. Suppose we have 0. Lambda is positive, so we don't want 0. So here's k should be natural number. Okay. So k is non-zero because a is positive. Okay, that implies a equals k pi over L. Okay, so finally, what do I have here? Lambda equals, if you assume lambda is positive, then if lambda equals, so if lambda equals k pi over L, square, k is natural number, then from here I have xx becomes b sine a equals k pi x divided by L. I have here. Suppose if lambda is not equals to k pi over L squared, okay, for any, then what? If lambda a is not equals to this one, then this cannot be 0. Okay, this cannot be 0. Then b should be 0, right? This cannot be 0. B should be 0. Contradiction. Okay. So in this case, if this is true, then xx should be 0. Okay. Or if I assume x is non-zero, b is non-zero, then there's contradiction. Okay. So if b is x over b1, b is non-zero. Or you can just remove here. Okay. Just the note right here. Note, and we want x is non-zero, and b equals 0. Then we're done. So okay. Then it should be 0. Okay, I can write that in this way. Either way is okay. So anyway, if alpha is positive, lambda is positive, we have only value lambda equals k pi over L squared, then we have non-zero solution. Okay, so we're done for lambda positive case. Okay, now if lambda equals 0, what happens? So case 2, lambda equals 0. We have nothing to do, right? So in this case, x double prime plus lambda x equals 0. This is 0. You have x double prime x equals 0. That implies fxx equals some ax plus b. Okay? And then since x0 equals 0, so that implies 0 equal x0, what is it? x0, b. So that b equals 0. And then xl equals 0 by condition. Then al. So from here, b equals 0, then you have xx should be ax. And then this should be 0. That implies a equals 0. So therefore, xx equals 0. This is just not we want. Okay? And then case 3, if lambda equals negative, then you can write the lambda equal minus a squared, and then a is positive. You can write that in this way. And then our equation becomes minus a squared, x equals 0. Again, your auxiliary equation. Our auxiliary equation becomes r squared minus a squared equals 0. R equals plus minus a. So if we have this solution of root of auxiliary equation, so that implies the general solution of ODE would be a e to the ax plus b times e to the minus ax. Okay? And then our condition x0 equals 0, xl equals 0. So then a plus b equals 0. You plug L. So a times e to the al plus b times e to the minus al becomes 0. So when you solve this equation, you only have a, b equals 0. It's easy to solve. I'm not going to spend. So that implies xx should be 0. Okay. So we separated 3 different cases. only case we have if lambda equals k pi over L squared, then we have only non-zero solutions. All other cases, we have zero solution. So therefore, so lambda equals k pi over L squared. So these are eigenvalue. So k, natural number, is eigenvalue, and x equal b is constant. I can just put sine k pi x divided by L is corresponding eigenfunction, because this is non-zero solution. Okay, that we're done. Okay, and problem A, the pair of solutions lambda and x satisfying this condition, we have only lambda equal k pi over L squared and xl equals sine k pi over x. And you multiply any constant in front of here. Any constant is okay. But I just, the simplest one is 1. Okay? So this will be used a lot. You already see that my previous lecture, we used the solution of this to find the heat equation, solution of heat equation, right? And then let me do B part. Okay, so problem B is this. You do the same thing what I did. 0, so x prime 0 equals 0, x prime L equals 0. Similarly, do the same. Case 1, lambda equals positive. This is lambda equals positive case. Then again, you got auxiliary equation. So let me try to write down clearly. So lambda positive case, again, lambda equals a squared. A is positive. And then from auxiliary equation, we have the xx, I just skip, and cosine ax plus b sine ax. Okay. And then let's take a derivative. So derivative of this guy minus a sine ax plus ba cosine ax. Okay, and then x prime 0 equals 0. That implies you plug x equals 0. Then x prime, what do you get? X prime 0 equals 0. And then from here, BA, you have a BA, right? So that, since A is non-zero, so that implies B should be 0. So then our xx equals b equals 0, a cosine ax. Okay. And then I'm using x prime L equals 0. And then you plug in L here. So from this equation, so we have minus AL sine, b term is gone, sine AL equals 0. Okay, so this is what we have. Okay, if A equals 0, if you take A equals 0, whole thing equals 0. We don't want. So here again, A is non-zero, so sine AL should be 0. Okay. So if A equals 0, then X equals 0. So we don't want this case. So that's why sine AL equals 0. So that implies AL again, K pi k pi. So k, again, a is positive, so integer. So this one. So therefore, we have a equals k pi over L. Okay. So here, again, if lambda equals k pi over L squared, k is integer, then xx becomes a times, you plug here, cosine k pi x divided by L. This is what we have. Okay. And then if lambda is different from k pi over L squared for any n, then xl, what is x? In this, if it's not equal to this, then this cannot be 0. Again, a should be 0. So therefore, a should be 0, then implies xx should be 0. Okay. So we have only this case to get non-zero solution. Okay. And then case 2. Case 2, lambda equals 0. Then again, x, I just skip, x double prime should be 0, xx equals ax plus b, ab a constant. Then x prime 0, x prime 0 equals 0 implies a equals 0. Okay, a equals 0, then x prime L should be also 0. So therefore we have xx equals b constant. So this satisfies x prime L equals also 0. So we have this solution. So lambda equals 0, we have this solution. So here we want b is non-zero. Okay. So the difference between previous example and B part is we remained lambda equals 0, we have constant solution. Okay. And then case 3. So case 3, lambda equals negative case. Again, lambda equals minus a squared. A is positive. You can write it down in this way. Then our solution also, in the previous case, we have e to the ax plus b times e to the minus ax. And then you take derivative of that a times a e to the ax minus b times a e to the minus ax. Again, x prime 0 equals 0, x prime L equals 0. That implies equation, let's see, a minus ab equals 0. Then L, exponential AL minus AB, E minus AL should be 0. So you solve this equation, A is non-zero, it's easy to solve. So you get AB, both should be 0. So XX equals constantly 0. So we have 3 cases. Then we have only case remained. Okay, this case and that case. So finally, so if lambda equals k pi over L squared, now I change k from k, k, yellow, so let me erase more. So then k equals 0, 1, 2, 3, da, da, da. So then if 0 equals 0, then lambda becomes 0. That's the case, case 2. Then xx becomes here a I remove constant, okay? I take constant both 1, then cosine k pi x divided by L. So if k equals 0, the cosine, this value becomes, if 0, then whole thing becomes 1, right? So actually this is the eigenvalue and eigenfunction of the second problem, okay? So here, this is important. So this will be used later when we have a problem. And then you can follow the same procedure for C and D, okay? So I don't need to do all for one. So you can follow the same method for C part. So x double prime x plus lambda xx equals 0, x from 0 L, x double x, what was it? Which one? Derivative, let's see. x0 equals 0. Yeah, x0 equals 0, x prime L equals 0. Then in this case, what we obtain that if lambda equals 2k minus 1 pi over 2L squared, k integer, then xx I don't write down the constant. Then we have sine 2L 2k minus 1 pi x. Okay, this is what we have. You will get this one. Actually, I explained in class 2. And then d part x double prime x plus lambda xx equals 0, x prime 0 equals 0, xl equals 0. So in that case, if let's see, I don't need arrow here. So if in this case lambda equals again 2k minus 1 pi divided by 2L squared, k integer, then xx now should be cosine 2L 2k minus 1 pi x. Okay, because you put xl, you have L, you plug L, cosine value becomes 1, derivative this becomes sine, this should be 0. So again, k is integer. Let me check whether lambda equals 0. So let's just to check. So if lambda equals 0, then x double prime equals 0, xx equals ax plus b, x prime 0 implies a equals 0, xl implies b equals 0. Okay, so lambda equals 0 does not include the both sides. Okay, so this will be the solution eigenvalue. So otherwise, so in this case, you can check by yourself if alpha is different from lambda different from this, then xx should be 0. Here also, if lambda equal different from 2k minus 1 to L pi square, then xx equals 0. Okay. So these problems, these solutions are very, very important. So why these are very important? Later on, I'm going to later on. So we are going to study this equations, heat equation. So U sub T equals, again, I remove xt. U T equals U xx plus some fxt, and then U 0 T equals gt, U L T equals ht, and then U x0 equals lx. Okay. So we are considering this problem. This problem, let's say 1. And then you can make another problem, the same equation, ut equals u xx plus fxt, and then I prime u difference with respect to x0 t equals gt. I just change boundary condition. X ux lt equals ht, and then u x0 equals lx. So this problem. And then I will also do another problem, number 3, the same heat equation type u xx plus fxt, and then I have here condition u 0 t equals gt, u x 0 t, not 0, xl lt equals ht, u x0 equals lx. Okay, I just change the boundary conditions. And then number 4, ut equals u xx plus fxt, u x0 t gt, u lt equals ht, u x0 equals lx. Okay, so L is given. These all functions are given. So f, g, h, l are given. So here where f, g, h, l are given. You need to find the solution uxt. So we have 3 different type, right? So in order to get solution of this, we need a problem, okay? In order to solve this, we need a B problem. This is B problem. In order to solve 3, let's see, what was the C problem? Problem C, yeah, C problem. Okay. In order to solve this one, we need the problem C. We need the problem D to solve this one. So that's why I explained the 4 different eigenvalue problems. So here, I cannot do all 4 cases. Once you know one of this case, how to solve one of these cases, you can follow exactly the same method. Okay, so next time I will discuss problem number 1. Okay, and then if I explain problem number 1, that you can follow exact the same method to get solution of problem 2, problem 3, problem 4. Okay, so here basically if I give some examination problems, I have just 8 options, right? Boundary condition. So we have for each 4 different problems with the same equation. Okay, so you need to get used to use this boundary value eigenvalue problems. So these eigenvalue problems are very basic. It's very important to get Fourier series solutions. Okay, let me stop here. Thank you very much.